When we analyzed our surface map, we contoured in lines of equal pressure called isobars. That is not the case on upper air maps because each upper air map involves a different constant pressure surface. So for example, on an 850 millibar map, the pressure across the entire domain is the same, 850 millibars. So the main contours on an upper air map do not involve pressure. Instead, they involve a product called geopotential height. I wanted to review the concept of geopotential height before diving in to our upper air maps. So again, at each mandatory level, 850 millibars, 500 millibars, 300 millibars, etc., we're dealing with a constant pressure surface. Say for example the 850 millibar map you see here. The pressure is 850 millibars across this entire map, across the entire domain. Geopotential height is the height of that constant pressure surface above mean sea level. Let's pretend that we could actually physically see the 850 millibar surface and that we are looking at it straight on. You might see something like this, where the blue line is our surface, we'll call that mean sea level, and the pink line is our 850 millibar constant pressure surface. Geopotential height is the height of that constant pressure surface above mean sea level, as denoted in green. Now, geopotential height changes based on variables like temperature, so that constant 850 millibar surface is not going to be the same height across its entire expanse. We're going to see variations in geopotential height of the 850 millibar surface, and that's what manifests itself as troughs and ridges on upper air maps. And when you hear meteorologists say height rises or height falls, they're referring to changes in geopotential height over time. So that's what makes geopotential height a useful variable for analysis on upper air maps. These main black contours that you see on upper air maps are lines of equal geopotential height, also known as isoheights or isohypses, and they will be given typically in units of meters. So for example, on this 500 millibar map, this bottom contour here is labeled 5820, which just signifies that the height of the 500 millibar surface above mean sea level along this line, or the geopotential height of the 500 millibar surface along this contour, is 5,820 meters above mean sea level. Sometimes you'll also see them given in decameters, which is just tens of meters. So for example, on this 850 millibar map, this contour here is labeled 150, which just means 150 decameters, which is the same as 1,500 meters.
Have you ever wanted to spend a full week chasing storms? We're opening up seats for another 2027 tour after our previous 2 rounds sold out almost immediately. You'll take part in daily forecast discussions, target selection, and the real-time decisions that shape every chase day. Seats are limited, and this tour is priced to make an unforgettable storm chasing experience more accessible. Click the link in the description below to reserve your seat before it sells out.
Another thing you'll see that's different from the surface map is that for many sources of upper air maps, of course they will contour in the geopotential height lines. That is done very similar to the isobar analysis we did on the surface map, where the geopotential height contours tend to follow the wind direction. But they often will also contour and shade in wind speeds. This is called isotach analysis. Isotachs are lines of equal wind speed, and they are contoured just like most other isopleths. On this sample 500 millibar map, the isotachs are these blue lines here, as well as the shaded regions. But unlike the isobars we drew in on the surface map, isotachs do not follow the wind direction. That might be slightly counterintuitive, but isotachs are simply contours that represent values of equal wind speed along them, and wind direction has no bearing on wind speed or the isotach analysis as a whole. Just like a surface map, upper air maps have station plots with important weather information on them. Upper air station plots are a lot less complicated than surface station plots can be, but there are some key differences that we need to know between surface station plots and upper air station plots. Here is an example of an upper air station plot, and for the sake of this example, we're going to say that this station plot was found on an 850 millibar map. As with a surface station plot, the value at the top left of an upper air station plot gives us the temperature at the station, but this time for upper air stations, it's given in degrees Celsius. Anytime you see a temperature on an upper air station plot, it's given in degrees Celsius. Now the value at the bottom left of the station plot is not the dew point at the station like it is at the surface. Instead, it's a parameter called the dew point depression, which is simply the difference between the temperature at the station and the dew point at the station. Again, it's given in degrees Celsius on upper air maps, and from the dew point depression we can find the actual dew point. All we'd have to do is take the temperature at the station, which is -5 degrees Celsius, subtract our dew point depression, and we'd get a dew point value in this case of negative 29 degrees Celsius. Now, some sources of upper air maps will show the actual dew point on their upper air station plots. This includes the Storm Prediction Center's upper air maps page. The way you can tell whether a source is displaying the dew point or the dew point depression is if you see negative values for that bottom left number in the station plots. If you see negative values, you know the map is displaying the actual dew point. Because the temperature is always greater than or equal to the dew point depression is always going to be positive. So if you see negative values in the bottom left of a station plot on an upper air map, you know that that upper air map is displaying the dew point instead of the dew point depression. Now, this value at the top right of the station plot is the geopotential height value at the station given in units of meters. This is the most complicated value on an upper air station plot. Number one, because like the surface map, it's given in code, but the way it's coded is different for every mandatory level of the atmosphere. Here is a chart that shows all of the ways that geopotential height values are coded on each of the different upper air maps we use to forecast. I'm going to include this chart in the attachments tab below this video if you'd like to reference this in the future. The difference among each level comes in which 3 digits of the actual geopotential height value are written in the station plot. Starting with the 850 millibar level, this top row here, the last 3 digits of the value are coded with the leading 1 dropped. So for example, if we have a value of 410 written in the station plot, we just add a 1 to the beginning of that to get our actual geopotential height of 1,410 meters. The same is true for the 700 millibar level. The last 3 digits are written in the station plot, but there's a difference based on the first digit that you see listed. Just like how surface pressure is coded on a surface station plot, if the leading digit is from 5 to 9, the leading 2 has been dropped, and if the first digit is between 0 and 4, the leading 3 has been dropped. So you can see in this first example, 970, that value, that first digit is between 5 and 9, so we would just add a 2 to the front of that to get our geopotential height value at 700 millibars of 2,970 meters. For this second value here, 030, we see that that first digit is between 0 and 4, so we would add a 3 to the beginning of that to get our final geopotential height value of 3,030 meters. Now at 500 millibars, the first 3 digits are listed in the station plot, and we simply add a 0 to the end of it. So for example, 558, those are the first 3 digits. We'd add a 0 to the end of that value to get our geopotential height value at 500 millibars of 5,580 meters. Same thing at 300 millibars, the first 3 digits are listed, and we simply add a 0 to the end of it. So for example, if you have a value of 900 listed on the station plot, just add a 0 to the end of it for a final value, in this case, of 9,000 meters. The 250 millibar level is where it gets a little bit weird. So the difference comes in whether your geopotential height value is below or above 10,000 meters. If the geopotential height value is below 10,000 meters, in most cases, this is going to mean that the leading digit is a 9. Then the first 3 digits of the number are listed, and we add a trailing 0. So in this case, 997, that leading value is a 9. It means it's below 10,000 meters, so we add a 0 to the end for a final value of 9,970 meters. If that value is above 10,000 meters, that's usually going to mean that leading digit listed is a 0. Then your middle 3 digits are used, and we add a 1 to the beginning of it and a 0 to the end. So in this example, I'll back this up for us here, 054, first digit is 0, it means it's over 10,000 meters, so we add a 1 in front and a 0 at the end for a final value of 10,540 meters. At 200 millibars, the middle 3 digits are used regardless, and we would add a 1 in front and a 0 at the end. So in this case, 176, add a leading 1, a trailing 0, for a final value of 11,760 meters. Now, in most cases, you're not really going to have to worry about this too much because upper air maps are typically already analyzed for you by the time you see them online. But it's good to know how geopotential height values are coded on upper air maps, just in case you may need to analyze an upper air map on your own. So in our example here, we have a geopotential height value coded as 430. Remember, this is an 850 millibar map, so we just add a leading 1 to this value for a final geopotential height value of 1,430 meters. The value at the bottom right of the station plot is the change in geopotential height at the station over the past 12 hours. For levels of the atmosphere below 500 millibars, so 850, 700 millibars, for example, this is given in meters, whereas for levels 500 millibars and above, so 500, 300, 250, and 200 millibars, this is given in decameters, which is just tens of meters. 1 decameter equals 10 meters. So in our example here, we're at 850 millibars. The positive sign indicates that the geopotential height has risen over the past 12 hours, and our value of 20 indicates that the geopotential height has risen 20 meters in the past 12 hours. Let's say instead of 850 millibars, this was at 300 millibars. Then this would be in decameters. Again, 1 decameter equals 10 meters. So this would mean that our geopotential height has risen 20 decameters in 12 hours, which is equivalent to 200 meters. And of course, if you had a negative sign here, that would mean the pressure has fallen in the past 12 hours. And then we have the wind barb, which is exactly the same as it is on a surface station plot. We just count the number of flags and add up the corresponding values of each. So in this case, we have 1 flag, which is 50 knots, 2 full barbs, which are 10 knots each, and then a 5-knot barb there with the half barb. So 50 plus 10 plus 10 plus 5 is 75 knots. And the direction, of course, is we go through the flags toward the center of the station. So this is a westerly wind at 75 knots. And the central station circle is not used for anything on upper air maps like it is for cloud cover on surface maps, so we can ignore it when looking at upper air station plots.
Remember to check out those links in the description below, and then watch another video.